research paper. Most of the vast majority of the introductory textbook treat Bayes' rule as an optional or as an extension of the conditional probability, and they mention Bayes' rule conceptually, briefly, at most 1 or 2 pages, the end of the conditional probability section, or totally completed omitted. Mainly due to the complexity of this formula. And at the same time that after we completed our research project, we had some open discussion with all of the faculty members who have taught Intro to Statistics, and most of them expressed their concern that Bayes' rule is still very foreign to them in terms of the thinking and also explaining the structure of the formula. Now, also based on the previous literature and the mathematics and the statistics education, and when you teach Bayes' rule, one of the most successful and the most effective way to present the topic is to teach the topic through interesting and practical examples. And indeed, this textbook does have Bayes' rule as an independent section besides a part of the conditional probability, provide some very interesting example that student can see how Bayes' rule can be applied to. And one of the most representative one is a medical screening test based on the test result. Whether or not a given person has or carries a disease, which is to say, medical term, calculating predictive value, positive, negative, based on sensitivity, specificity, and also prevalence of those diseases. And one of those newest textbook include one of the very interesting the example, and I believe this one become very famous, Monty Hall problem, and I believe this is the let's make a deal. There are 3 doors, and one of the door has a sports car, the other one has a goat, and should I switch my choice to increase the chance of winning sports car or not? And I thought this was a very interesting. And while my co-author and I appreciate the practical value of such example, but we need to come up more interesting and creating a more realistic scenario. And that is one of the motivation that we wanted to provide an example pertaining to legal decision making, which means a criminal law. Given that there are so many TV shows and the movies nowadays that highlight criminal law and investigation that leads to the verdict of the defendant, guilty or not guilty at the criminal court, I thought this would captivate the student's interest, and then we'll be able to make them see how Bayes' rule can be applied to determine defendant's guilt status. So in the end, what I briefly mentioned, we wanted to know experimental group, which means that teaching Bayes' rule through our hypothetical yet realistic scenario perform better, which is a competency, than their counterparts in a control group, which means the Bayes' rule is taught in a traditional way using typical examples such as medical screening test and others. And at the same time, we wanted to see that if there's any significant difference in attitude toward Bayes' rule and between those 2 groups. And lastly, what are the pedagogical merits? And those are the 3 main research questions that we wanted to answer and we wanted to show you. The first, abstract. And one of the most important things about the teaching of Bayes' rule, unlike traditional classical statistics, is Bayes' rule has some nature. It's called a cumulative nature of the evidence, and which is much more practical as compared to classical statistical method, such including t-test or z-test or ANOVA, and based on p-value by Fisher's p-value and Neiman-Pearson's testing hypothesis, alpha value based. And those classical statistics operate in a terminal way. So basically, the p-value is, based on the null hypothesis is true, and what is the credibility of the evidence, what was actually observed in the sample. And it's just like you can't really combine unless you use a meta-analysis, which is such a highly sophisticated topic for statistical novices. So we wanted to see or show cumulative nature of the Bayesian. And that's our emphasis, number one. Now, also philosophical foundation, what made us motivate coming up with a legal decision-making philosophically is that one time that I was reading George Pollier's Plausible Reasoning textbook, which published way back in 1958 or 59, and I came across a very interesting philosophy. Although he does not say this is a Bayesian, but I came across a very interesting reasoning pattern, which means examining several consequences in succession. So based on what was actually observed in all pieces of evidences, such as I put down B subscript 1 represent the first evidence, B subscript 2 the second evidence, and so on. And using those evidence to prove your conjecture. So our example, conjecture represent defendant is guilty. So evidence B1, B subscript 2, those are represent some of the solid evidence presented at a criminal court trial. That includes fingerprint and the blood type and DNA evidence. And then how does strength of the evidence affect our conjectures? So that's one thing that I thought that this would captivate students' interest and promote their learning of the subject matter to a further extent. Now, relevance of the Bayes rule to hypothetical legal scenario, and we came up with this very interesting example, which probably students may well be very familiar with those TV show. And the body of the 22-year-old woman found stabbed to death, Western Massachusetts home. And there is a sign of the struggle evident in the room, on the body, and no evidence of sexual assault. And the blood stain is found in the area of the surrounding where the body was discovered. And based on the investigation, they found that suspect has blood type O and the Caucasian, and at the same time the fingerprint left at the scene, and also DNA research was done. So those are the three pieces of evidence to determine whether or not defendant is guilty. And what I mean by guilty means go beyond above reasonable doubt. Now, there is some Bayes rule, modified Bayes rule equation, and I'm going to show you three of them. And the first one is G represent the guilty, and the vertical line, as you know, given the EN, E stands for the evidence, and the subscript of N indicates the nth evidence, which we consider nth evidence is the newest evidence. And the H is the all evidences prior to nth evidence, which means E1, E2, E3, all the way up to including E subscript of N-1. So this formula was given one of the previous literature that we came across, Finkelstein and Stephen Goodman's article pertaining to law decision making, and we decided to use this equation. For instance, suppose that you are going to evaluate defendant's guilty status based on the first two evidences. So when you evaluate second evidence denoted by E subscript 2, and all of the jurors have already completed evaluation of preceding evidence, namely E subscript of the 1. So using equation number 1, plugging back, this is going to be such formula, although it looks very complex, but I was patient enough to walk students through and representing, explaining each component that constitute this equation using our hypothetical case scenario. And this is one that many literatures suggest that there isn't a way to translate probability into odds ratio, and that would actually make students understand the concept slightly better, especially the hypothetical case scenario that we are using. Guilty is more likely to be not guilty how many times, and at the same time the student having a very tough time distinguishing two conditional probability. If you take a look at the left hand side, right, G given the EN and the H, so which means the pre-existing condition is evidence. That is to say, this probability would generate probability of the guilt status based on what was actually observed in evidences. And the right-hand side of the second component, this is the pre-existing condition is a guilt. So on the presumption of the guilt, right, how credible this newest evidence is, and often that a student having a very tough time distinguishing given that statement. This is based on my previous teaching experience. So separating those two different types of conditional probability, at least the student can see those are conceptually quite different probability. At the same time, that just having fraction, I could translate probability value into odds ratio. Now, we're going to go through quickly, and there are three types of evidences. First one is a blood type matching. So we just started out probability guilty is a 0.5. The one of the reasons is it is very hard to give a correct interpretation of presumed innocence, which means that before you see actual first evidence, what is the chance that this defendant is guilty? So we conducted some informal survey, and vast majority of the students say it is reasonable for us to state presumed innocence as a 0.5, which means a neutral position. And then I was quite shocked, actually, that I thought that people would say presumed innocence is probability of the guilty is equal to 0 or close enough to be 0. But obviously, the Bayes rule would not work if you plug in probability of the guilty is equal to 0. So I'm quite happy about that. So given our assumption and a student feedback, suppose that Caucasian with a blood type O is a 0.45. So this is a more like a general probability. This is equal to the frequency of that particular type. So 0.45 here. And then we're going to start out guilty 0.5, meaning not guilty is complement of the 0.5. So we're going to plug in the formula into the equation number 1, and it comes out to be 0.69. So this means that based on what was actually observed in the first evidence pertaining to the blood type matching, at this time, guilt status is 69%. So as you can see, after they saw first evidence, 0.5 is increased by 0.19 now, increased to 0.69. And plug that numbers into Bayes factor. The Bayes factor is a credibility of evidence on the presumption of the guilt as opposed to presumption of not guilty. So this is a 2.22. And then we are going to plug the numbers into the posterior probability, which means that based on what was actually observed, the first evidence, what is the chance that this defendant is guilty to not guilty? And clearly the 0.5, 0.5, so Bayes factor happens to be identical to posterior odds ratio. So what is the interpretation, which I told the student and try to give some interpretation. And this means that probability of the defendant being guilty has increased from 0.5 to 0.69. Also, Bayes factor 2.22 reveals the credibility of the first evidence, blood match, is 2.22 times greater than under the assumption of the guilty than it is under the assumption of not guilty. So in other words, if you actually reconstruct combining Bayes factor and also it's called a prior probability, this would produce posterior probability, and the end of the first evidence, defendant is 2.20 times more likely to be guilty than not guilty after seeing the evidence E1. Evidence E2 is a fingerprint analysis. So you can see after we plug all of the information into the equation, and remember that Bayes rule, as I said, illustrating a cumulative nature of the evidence, which means when you actually evaluate evidence, second evidence, all of the jurors have already evaluated preceding evidence. So now we are going to use 0.69 as a prior probability, no longer not the 0.5. So this is a cumulative nature, which is very practical. And then clearly all the others, we're going to plug all the number into the equation that I showed you, equation 1, 2, and 3. This time Bayes factor came out to be 4.76. So credibility of the second evidence based on presumption of the guilty and the completion of the evaluation of the E1 is 4.76 more than presumption of the not guilty. And then we found out the probability, posterior probability of the defendant being guilty, combining those two evidence comes out to be 0.914, which is getting higher and higher. And then we're going to plug those numbers into posterior odds ratio, 10.60, which means the posterior odds also reveals the defendant is 10.6 times more likely to be guilty than not guilty after seeing the evidence, E1 and E2. Now, last one is the DNA analysis. And one of the reasons why that we decided to include the DNA, meaning that prior to our discussion of the DNA, vast majority of the statistical novices, which means the students who are currently taking intro to STAR, they believe DNA is the one determining guilt of the defendant. But the DNA really does not calculate the probability that defendant is guilty. Rather, DNA calculates credibility of the evidence on the presumption of guilt or on the presumption of the not guilty. So the pre-existing condition is different. So I wanted to make sure to make them see those are not posterior probability. So that way that they see, they will be able to make a distinction between E given G from G given E. So that is one of the reasons why that we decided to include the DNA. So going through all of the DNA analysis, and the posterior odds came out to be 625.17. So the defendant is guilty at 625.17 times more likely to be guilty than not guilty. Now, also I wanted to show students that what if we started out other than 0.50 as presumed innocence? So those prior probability does affect the posterior probability. So I showed those summary of the table, and clearly the posterior probabilities largely affected by prior probability, which has subjective nature. And we started out at 0.50, but if you started out 0.25, your final probability would be 0.995, and the 0.01 generate 0.863, and the 0.001 generate only 0.384. Now, pedagogical value. And I conducted some empirical research, and a sample of the 88 students, we split the 88 students into 2 different groups. And although these are 3 sections, but one group is a standard group. So we teach Bayesian through typical textbook example without using our legal scenario. And the other 2 sections, we implement our legal scenario into classroom teaching to present Bayesian statistics. And then we wanted to see their attitude change, which I briefly mentioned very beginning of the session, and their competency, and how extensive they demonstrated their knowledge regarding Bayesian's Bayes rule. So findings between 2 groups. Pre-test, before we present those legal scenario, we did not see any significant differences. But at the end of the research studies, we found that post presentation, which is after we presented legal scenario, experimental group shows higher positive attitude toward the topic of the Bayes rule compared to their counterparts in a standard group. And the p-value is very small, less than 0.001. And then pre versus post attitude within the same group. And first pre, we don't see any significant difference for both groups. But the post group, post presentation case study group has much more significantly higher positive attitude based on their response of one of those 4 questions pertaining students' interest in the example use, engagement with the class material, and the curiosity and the perception of the Bayes rule is applicable to real life situation as compared to students who are in standard textbook presentations. And the competency, so we gave them 3 questions quiz. And clearly the case study group who are taught Bayes rule by legal scenario did significantly better than their counterparts in the standard program. And the faculty feedback and a post-survey, vast majority of the faculty member after research project, we had open discussion. They were quite impressed and introducing a Bayesian in this way using realistic yet hypothetical, or hypothetical yet realistic example is one of the most effective way to present such complex concept. But one faculty member and then 2 other faculty members expressed their concern presentation of the Bayes rule is too much when they teach introductory statistics. And that is the reason why they usually omit Bayes rule and the conditional probability. One of the reasons is that statistical novices tend to exhibit greater anxiety toward the subject matter, much more than others. And then that is the reason why they rather want to spend more time in normal distribution or testing the hypothesis. So they all omit probability, or they briefly provide the conceptual basis of the probability. And all mathematics and statistics faculty members who are open to teach Bayesian thinking, they said that our hypothetical example is intellectually challenging and stimulating in every aspect. And the author's comment is presenting Bayesian using a legal scenario, clearly that this would help students, even statistical novices, see the cumulative nature of the statistical method. It's not, work in a terminal way. And then, second evidence is contingent upon first evidence. And when you reach the third stage of an experiment, these are contingent upon all preceding evidence. And this is a more like a research nature. And it's not like a first evidence is mutually exclusive to second, mutually exclusive to third. And the nature of the research works in a cumulative manner. So that would help students develop two very important reasoning components. That is what we call deductive reasoning, general concept to specific. That is basically the classical statistical approach, p-value and the Neiman-Pearson's null hypothesis testing. And we never introduce inductive reasoning, going from specific to derive general concept. And that is a very, very important reasoning for everybody, regardless of what they study. So that is the one of the things that I would like to continue to emphasize on those two reasoning through presenting conditional probability and Bayes rule. And this concludes my presentations. Hello.
Sorry, I forgot to unmute myself. Thank you. That was a very interesting presentation. We did have some questions throughout the presentation, so I'll ask a few of those. And then we do have someone with their hand raised, so I'll let him speak in a moment for himself.
Okay.
But one of the questions was about how much time do you spend on probability in this course, and how much time did you spend on Bayes' rule, which I think you addressed the second part in one of your slides, how much time you spent on this, but I didn't remember the answer.
Yeah, prior to the presentation of the Bayes rule, we went through, I was the one who taught every single 3 sections, and then I covered addition rule, multiplication rule, and then conditional probability, very basic one, given that, and then also the complement rule, at least one or more. So basically I covered all of the basic elements of the probability. So I would say good 5 to 6 lectures I went through prior to the presentation of the Bayes rule. So all of the students, regardless which group they are affiliated with, they have had some good working knowledge of the probabilities.
Okay, great. And I'm going to unmute Mark. He had a couple of questions during the presentation, and he has his hand raised, so it might just be easier to let him ask those.
Okay. Hi, Mark. How are you?
Yes, quite good. I was wondering, I don't know much about Bayesian statistics, but I was wondering if you invoked the 3 evidences in a different order, would the results, the final results, be changed?
That is a very good question. If I ever reorder, one of the reasons why that I order the way it is that usually the blood type analysis is not really strong enough. The blood type testimony would never be strong enough to confirm defendant guilty. And so I basically started out very elementary, which means a very primitive order, though. Even prior to the DNA evidence's popularity, even back then, 1800 or 1900, they always start out the blood type first, and then they move on to the fingerprint. So I'm not really a legal expert, but based on all the literature I have read, this is the way that they usually order. But going back to your questions, may well be, because if I ever would have started out the DNA evidence first, then pretty much I would expect the Bayes factor to be very big, because people have a misconception about the DNA evidence, which I briefly mentioned. People believe the DNA evidence is the one that calculates guilt status of the defendant. But even so, if I ever studied out the DNA evidence and then followed by fingerprint and then also blood type, I would say posterior probability, the end of the first evidence, would be very big and it gradually goes down. So I'm not quite sure that mathematically speaking, I would expect the answer would come out to be same, but realistically, maybe different.
If I may add a remark, it would be quite easy to calculate the six different orderings, E1, E2, and E3.
Right. So the combination of the E1, E2, E3, E2, E1, E3, E3, E2, E1. Yeah, I have never done that.
All right.
Okay, well, thank you for our both of sets of our presenters today, and thank you to our audience for posting such thoughtful questions. I want to make a few announcements. There should be a announcement coming out soon about the November JSE webinar, and then I'd like to also remind you that when you finish the webinar, when you sign out of the webinar, you'll get a prompt for feedback, and we'd love to have information about how we're doing, or if you want to provide suggestions for how we can improve your experience, please let us know.